Computing with NVIDIA GPUs, so I don't want to focus on performance on a single chip. I want to focus on features which allows you to build, to develop applications which are very scalable, like the Chinese Academy for Science did. They announced last year an application performance for molecular dynamics simulation of up to nearly 2 petaflop sustained performance, and this is possible with the features we introduced and we have in use in the current GPU ecosystem. So, from the outline of this talk, I would like to introduce a little bit the multi-GPU programming. Focus later on communication technologies inside a single host with multiple GPUs, communication technologies for multiple hosts, multiple GPUs. We heard from Professor Panda yesterday about GPU-aware MPI implementations. I would like to focus a little bit on this. And last but not least, I would like to talk about some NUMA effects, which of course affects also the GPU like any other devices inside the node. So what about multi-GPU programming? In the past, a lot of applications are started with the programming of GPUs within a single node with a single GPU, but we see more and more developments for multiple GPUs in multiple nodes for real scalable cluster implementations. So it's not only in the academic space like we see with GROMACS, it's also in the commercial space like Abacus, where Simulia provided a multiple node, multiple GPU implementation in the last release. So there are a lot of advantages for the usage of multiple GPUs. One, you have, of course, more memory in total, so you can calculate larger problem sizes. You have more processing power, of course, so you get faster your results. And multiple GPUs per nodes also improves the performance per watt ratio. If you have a taxonomy of the inter-GPU communication cases, you have single and multiple nodes, you have single processes and multiple processes, and for the single nodes you can at the moment use peer-to-peer protocols, and the GPUs can communicate via host memory. I will go a little bit more in detail later. And for multiple GPUs, you are using host-side message passing like MVHP or Open MPI, which was introduced also yesterday. I will also cover this on the next slides. So many scientific applications are using the decomposition technologies. I believe you are all aware of this. So the model geometry will be decomposed and the partitions will be sent to independent compute nodes on a cluster, and the compute nodes operates more or less independently, exchanging the results with the other nodes via MPI, and you get at the end a complete result. And with a hybrid model, partition will be also mapped to the GPUs, and the GPUs support the CPU computation. So nothing magic, it's a normal hybrid model where the GPUs are supporting the CPUs in the computation. Communication mechanisms, technologies for single host multiple GPUs. So in CUDA 4.0, we introduced a way that a single CPU thread can handle multiple GPUs. It's very easy from CUDA 4.0 on. So before, if you wanted to use multiple GPUs, you had to use also multiple CPU threads. So there's one call, CUDA set device, and with this call you can change the current GPU, and here is an example with a CUDA set device 0. You start following kernel on the GPU device 0, and you can also start, for instance, asynchronous memcopies, and then you change to the device 1 to the GPU 1 and start again additional work on the GPU 1. So it's very easy from a single CPU thread to handle multiple GPUs. One very important feature, which is a basis for many features, which I will introduce later, is a unified virtual addressing. You see here in the picture on the left, before CUDA 4.0, the data which were allocated on different devices like the CPU or different GPUs had their own memory space, their own address space, and with the introduction of the unified virtual addressing, all data which are allocated from the different devices have a unified virtual address space, which means that the driver or the device can determine from the address where the data resides. So it requires 64-bit Linux or Windows. It requires the Fermi architecture, and of course, as I mentioned before, it requires CUDA 4.0. What does it mean? A GPU can dereference a pointer that is an address on the other GPU, or can also dereference a pointer that is an address on the host CPU. There are two interesting aspects. It's a peer-to-peer Memcopy, which is possible with this mechanism. You see the direct transfer on the right. With a CUDA Memcopy, you can directly copy data from the memory of GPU 0 to the memory of the GPU 1 via the PCI Express. So the host memory is not involved, or the CPU at all is not involved in this transfer. The other aspect is you can direct access from one GPU the data in the memory of the other GPU with a load and store operation, and that's very easy. Before the introduction of these features, all the Memcopy operations had to be done through the memory of the host system. Both requires peer-to-peer access to be enabled, and there is it's not possible to have this peer-to-peer if one of the GPU is a pre-Fermi GPU, or if one of the GPU is behind another I/O hub chip, because QPI does not support the peer-to-peer protocol, the PCI Express peer-to-peer protocol, which we show in this slide here. You have two GPUs connected to an I/O hub, so peer-to-peer protocol communication is possible between the GPUs which are located on the same I/O hub. But if the I/O hubs communicating via QPI, the peer-to-peer process is not possible for the communication. So if you look to your architecture of the system, you have to be aware of this issue. And the issue here is explained in the Intel documentation, so that's not a issue from NVIDIA's point of view. It's an Intel issue that they don't support the peer-to-peer PCI Express communication. PCI Express switches are fully supported. In this case, we have one I/O hub and two PCI Express switches. The best peer-to-peer performance can be achieved between the GPUs which are located on the same PCI Express switch, but peer-to-peer communication is also possible, and I will show you the performance in a slide later between the GPU 0, for instance, and GPU 2, which are located on different PCI switches. How does peer-to-peer Memcopy help multiple GPU? So it's, of course, ease of programming. No need to manually maintain memory buffers on the host for inter-GPU exchanges, and it increases the throughput, especially when the path does not include an I/O hub. So in this case, you see here two GPUs are connected via PCI Express and located on the same PCI Express switch. We get a single directional transfer rate of up to 6.3 gigabytes per second. A duplex transfer, we also achieve 12.2 gigabytes per second. And the GPU pairs can also communicate concurrently if the paths don't overlap. In conclusion to the peer-to-peer throughput, you see here some numbers. I already mentioned the GPU throughput when the GPUs are located on the same PCI Express switch. 6.3 and 12.2 gigabytes per second. If you are communicating the blue line via the I/O hub chip, the transfer rate will be reduced from 6.3 to 5.3 gigabytes per second. And if you have to go through the host when the QPI link is between I/O hubs, then it will be reduced from best case 6.3 to 2.2 gigabytes per second, which is of course a lot of bandwidth which you lose. In CUDA 4.1, we introduced a new feature called CUDA IPC. I mentioned before, single threads can share multiple GPU or can communicate via peer-to-peer with the GPUs. So the IPC mechanism allows you the peer-to-peer communication between multiple CPU threads, which handles multiple GPUs inside the nodes. So you create a handle to a GPU device memory segment, which can be exported to another process within a node, and you can then use the peer-to-peer protocol between these processes in order to exchange data between the GPUs. It's already supported, this mechanism, by MVHPISH, like we heard yesterday from Professor Panda, and it's currently restricted to devices which supports the unified addressing, which is of course needed, and currently on Linux operating system, so not on the Windows system is this feature available. Communication for multiple hosts, multiple GPUs. We heard about GPU Direct. NVIDIA worked together with Mellanox some years ago. And what does it mean? So before GPU Direct, you had to copy the data from the GPU buffer to the network buffer inside the host system, inside the host memory, and with GPU Direct, this was no longer needed. You could, or both the network buffer and the GPU buffer could share region inside the host memory. So one copy operation was no longer needed. Currently, it requires transferring GPU data to and from the host CPU memory if you want to transfer data from a GPU in one node to GPU in another node. There's some work underway to use peer-to-peer. The peer-to-peer protocol, like inside a node, also for the communication beyond the node boundaries. I will cover a little bit later the MPI aware implementations for the GPUs. The first implementation of GPU Direct was based on a patch that's no longer needed. So with CUDA 4.0, we introduced an environment variable which allows you to this interoperability between the CUDA pinned memory and the InfiniBand. You have to set the CUDA NIC interop environment variable to 1. This is no longer needed with CUDA 4.1 because that's a default behavior. If each node has also multiple GPUs, you can continue using the peer-to-peer protocol within the node, and also some PCI Express transfers with the network communication can be overlapped in addition to the kernel execution. GPU-aware MPIs, we heard a lot yesterday in the talk from Professor Panda. What does it mean with the introduction of unified virtual addressing? The MPI implementation knows when they get a pointer where the data resides, if it is in the GPU memory or if it is, for instance, in the host memory. And it enables MPI send or MPI receives from or to GPU memory without exposing low-level details to the programmer, as mentioned yesterday. So there are some implementations, NVIDIA, Open MPI, also Platform MPI. They announced a beta version at the last supercomputing. So you saw yesterday these mechanisms, code without MPI integration. You have to use a CUDA Memcopy in order to bring the data to the right location, and then you can MPI send or MPI receive. And with the MPI integration, this CUDA Memcopy will be done by the implementation. So, as we heard yesterday, there are a lot of features implemented in the MBA pitch 2 implementation, point-to-point collective operations, pipeline data transfer with optimizations, overlap CUDA copy and RDMA transfers, supports GPU direct inside the node and also the CUDA IPC. All possible combinations of source and targets, so you can communicate between two devices, two GPU devices, between the device and the host, and you can also communicate between the host and the device. Open MPI, there are some features implemented which are GPU aware, but the implementation from Ohio is by far the most advanced GPU-aware MPI implementation. So you can use device pointers in order to send and receive, and most of the collective APIs are also supported, but not the collective reduction, and also not the one-sided API. The code which was contributed by NVIDIA is available in the Open MPI trunk on this address, and you will find more details in the Open MPI FAQ, and you can have a look. There are a lot of questions often how to compile the CUDA and MPI applications. Use the NVCC or use the MPI compilers, and best practice is in most cases to compile the kernels or the wrapper for the kernels with the NVIDIA CC compiler, and to compile the program with the MPI calls and the CUDA runtime calls with the MPI CC. Include the CUDA runtime header and link this together with MPI CC and link the CUDA runtime library to the application. Some words about NUMA. Of course, as we have seen before, the NUMA affects also the PCI Express transfers throughput, especially in dual I/O hub systems. Transfers to remote GPUs achieve lower throughput through additional QPI hops. So this affects, of course, not only the GPU, this affects every I/O device like network cards and so on. So when possible, locks the CPU threads to a socket that's closest to the GPU's I/O hub. You can use, for instance, task set, NUMA CTL, COMP, CPU affinity, or KMP affinity. Here are two examples for task set and NUMA CTL to bind a GPU application to a socket which is near, in this case, to the device, to the GPU device 0. Here's another example with a C function which uses a so-called scheduled set affinity system function. So you use a macro CPU 0 and CPU set in order to put the CPU cores into the affinity set, and then you use a schedule set affinity call to make this affinity set available. For some applications, it's not practical to restrict GPU to memory transfers to the memory of the single CPU socket, so you have to use alternatives like NUMA CTL interleave equal all for your application, or on some systems you have BIOS settings to minimize the difference between using near memory and far memory. So it's dependent from the systems you have in use. Also, many MPI implementations or also many resource management systems are using HWlog, and when you concerned about the NUMA topology with GPUs, you should also use or have a look to HWlog. It handles also PCI devices like GPUs, and it has a built-in support to get topology informations for CUDA devices. So, for instance, with an interaction between HWlog and the CUDA driver, you can get a list for instances or get a list for processors which are near the NVIDIA GPUs. So you have to have a look on this website, and it provides you a lot of features which you can use when you are concerned about NUMA topologies. There are, of course, development tools available which you can use in a cluster. For instance, the Alenia DDT and the Total View Cluster Debugger, which allows you also multi-GPU debugging support, which provides MPI and CUDA support for GPU clusters. Also, if you need a profiler, you can use the Vampire tool from the University of Dresden, which provides you the visualization and analyzes functionality for MPI and CUDA code. Other profiler partners are, or tools are Tau, PAPI, and the HPC toolkit. This brings me to the conclusion. CUDA provides a number of features to facilitate